Good evening to everybody. So, I would like to I would like to thank Parvista for arranging such a seminar. My topic is non-Hermitian system with balance loss and gain. So, let's start with some basic of quantum mechanics. So, in quantum mechanics, we have a state function psi which contains all the information that can be obtained about the quantum system. And corresponding to every physical observable in classical mechanics, we have a mathematical operator in quantum mechanics. So we operate the operator on the state which gives us the result of our experiment. And the time evolution of the system is obtained by solving the time Schrodinger equation. Here it is a Hamiltonian operator, and this eigenvalue of an operator is known as spectrum. The state of eigenvalues of Hamiltonian operator. Yes, sorry. Okay, so there must be some time lag. Okay, the set of eigenvalues of H at the Hamiltonian operator is the energy spectrum. As we know that the eigenvalues of a Hermitian operator is real, so for a spectrum, we need an Hermitian Hamiltonian operator. So, but here we discuss question that each hermiticity is essential condition for the real spectra. So let's start with example. So consider the Hamiltonian H as shown in equation 2. You can clearly see that H is a non-Hermitian matrix, and a matrix can be used as an operator. So this Hamiltonian represents a two-level system describing the physics of two coupled sites with gain and loss. Why I call this Hamiltonian as a loss Hamiltonian? So in this slide, I have plotted time evolution side by side by showing the time dependent Schrodinger equation for the Hamiltonian H, and for gamma 1 greater than gamma 2, and in both the cases we have considered that the modulus of k greater than the average value of gamma 1 and gamma 2. So when gamma 1 is greater than gamma 2, we see that norm, basically psi I, increases with time, and so gamma 1 is the gain parameter, and the system now acts as a gain system. But when the reverse happens, that gamma 2 is greater than gamma 1, and then the psi decreases with time. So now this is a lossy system, and gamma 2 acts as a loss parameter. Now, what happens when the gain or loss are balanced? That is gamma 1 equal to gamma 2. So when gamma 1 and gamma 2 is equal, that is the loss gain is balanced, and for a specific condition we get a stable solution, and psi oscillates with time. And now we represent the Hamiltonian as A, because we want to differentiate it with the balance loss gain Hamiltonian and Hermitian Hamiltonian. The A is written in the compact form, terms of the Pauli matrices sigma 1, sigma 2, sigma 3, and if we evaluate the eigenvalue, that is lambda plus minus equal to plus minus root over mod k square minus gamma square. Clearly, it is seen that the eigenvalues are real when mod k is greater than gamma. So in this plot, I have plotted the imaginary part of the eigenvalue with respect to the ratio of gamma by k. And whenever the ratio goes beyond 1, we uh, get the complex eigenvalue. So before that, when mod k is greater than gamma, we get the real eigenvalues. So hermiticity is not the essential condition for the real spectra or the real eigenvalue. Now, this kind of Hamiltonian can be grouped as pseudo-Hermitian Hamiltonian. So let's give a brief introduction about pseudo-Hermitian matrix. So suppose we have a matrix which is eta pseudo-Hermitian. That means Q dagger is equal to Q eta inverse, and Q admits entirely real eigenvalues for a positive definite eta. And if eta is equal to I, which is also positive definite matrix, then it reduces to the definition of Hermitian. So pseudo-hermiticity is the generalization of the hermiticity. And now pseudo-unitary matrix U. So the definition of pseudo-unitary matrix U is U dagger eta U is equal to eta. So even in this case, when eta is equal to identity matrix, then U dagger U is equal to identity, which is basically the unitary matrix. So it is also the generalization of the unitary matrix. As unitary matrix can be represented as exponential of I into some Hermitian matrix. So similarly, pseudo-unitary matrix can be represented as U is equal to exponential of I into some pseudo-Hermitian matrix. So in our present case, so A is a pseudo-Hermitian with respect to eta, which is given in equation 4. And both k and alpha belongs to the complex number. So you can see that you can calculate that eta is positive definite. That means eta is only real eigenvalue for mod k greater than gamma. So for the same condition, A also shows the real eigenvalue. So basically, a matrix can show real eigenvalues when it is pseudo-Hermitian with respect to some positive definite eta. Now let's see the calculation of expectation value in quantum mechanics. So say Q is a pseudo-Hermitian operator. Now the expectation value of the Q is given by psi bra Q and then psi ket. Now if we determine the complex conjugate, which basically gives psi bra Q dagger psi. Now for a pseudo-Hermitian operator, Q dagger not equals to Q, and then the complex conjugation of the expectation value will not be equal to the expectation value. So that means the complex expectation value is not real. This cannot happen because the expectation value must be real. I mean that the observable must be real. So there is some error in this calculation when we consider a pseudo-Hermitian operator. So we have to define the inner product in such a way that this expectation value gives the real result. So we define the inner product as psi eta psi. So psi bra eta and then psi ket. So now the expectation value of Q is obtained as psi bra eta, q, and then psi k. And if we get the complex conjugation, then you can see that we get psi bra, q dagger, eta plus, and psi ket. So as q dagger eta is equal to eta q, which gives the complex conjugation of an expectation value, and the expectation value both are equal. That means it is real. So all these calculations are the generalization of our known quantum mechanics in our textbook up to MSc. And whenever eta is identity, we get the known result which is read in our textbook. Now comes to our research work. So we have used the property that corresponding to the pseudo-Hermitian matrix, we can construct a pseudo-unitary matrix, and we have used this property to obtain the solution of a balanced Lagrangian nonlinear Schrodinger equation. So the Lagrangian density of our system, that is the nonlinear Schrodinger equation with balanced Lagrangian, is given here. And here both psi1 and psi2 are the complex scalar field. And we study the non-Hermiticity in a field equation. So you can see that all the terms are Hermitian except this psi dagger a psi term in our Lagrangian density. So the complex value of Lagrangian density due to the presence of A and the Lagrangian are embedded in the matrix A. So if we solve the Lagrangian and we get this equation as shown in equation 5, this basically represents the nonlinear Schrodinger equation with balance, loss, and gain. And you see that the A we have already discussed the balance, loss, and signature in A. This kind of nonlinear Schrodinger equation is important in context of mathematical modeling. It appears in the field of optics in nonlinear media, plasma physics, gravity wave, etc. And the potential term is relevant while modeling the Bose-Einstein condensation in mean field description. Now we solve the nonlinear Schrodinger equation via a pseudo-unitary transformation. We consider a pseudo-unitary transformation as psi is equal to u phi, where u is exponential of minus iat. As is pseudo-Hermitian, as discussed earlier, u is pseudo-unitary. So we call this transformation as pseudo-unitary transformation. This transformation basically maps psi into another complex scalar field at the same time t. And after this transformation, so the equation of motion for phi is given in equation 7. You can see that due to pseudo transformation, the balance log term which was given by the matrix A is removed at the cost of modifying the nonlinear. And now we solve the phi equation, that is the equation 7, considering phi is equal to w rx exponential of I theta x minus et. Here w is a complex constant column vector. So plugging the expression of phi into equation 7, which gives a couple of equations that is given in equation 9, 10, and 11. For a given potential, we can solve equation 9, and then solving this equation, we can get the solution of our original equation, that is the balance Lagrangian equation. So here we have presented one example, that is the quadratic potential, and the explicit expression of the psi given in equation 12. and this is the graphical representation of the solution. So in summary, so we have shown that a non-Hermitian Hamiltonian give real spectra. I have given a brief introduction about pseudo-Hermitian and pseudo-unitary matrix, and then we have introduced the nonlinear Schrodinger equation with balance loss gain, and then using a unitary transformation, the balance loss gain part is removed at the cost of modifying the nonlinear term, and then again considering a similitude transformation, we solved this nonlinear Schrodinger equation and presented a solution of nonlinear Schrodinger equation with quadratic potential. Thank you. I am happy to answer any question.